Every day, over 100 million barrels of crude oil are consumed worldwide. Today, we'll explore crude oil, also known as petroleum, a vital fossil fuel that drives industrialization and energy production. Primarily composed of hydrocarbons, its chemistry plays a key role in refining, fuel quality, and environmental impact. Formed over millions of years from decomposed organic matter, crude oil is a complex mixture of compounds. In this video, we'll cover its formation and composition, refining process, environmental impact, and various applications. Crude oil forms through slow geological processes over millions of years. It begins with the accumulation of organic matter, primarily microscopic marine organisms such as plankton and algae, on the ocean floor. Over time, these deposits become buried under layers of sediment, where they are subjected to heat and pressure. In an oxygen-deprived environment, bacterial activity transforms the organic matter into kerogen. As burial depth increases and temperatures rise, kerogen undergoes thermal decomposition, turning into crude oil. This transformation occurs within a temperature range known as the oil window, typically between 60 degrees Celsius and 120 degrees Celsius. If temperatures exceed this range, hydrocarbons continue breaking down into lighter gases, leading to the formation of natural gas instead. Crude oil is composed predominantly of hydrocarbons, which are molecules consisting of carbon and hydrogen. The three primary classes of hydrocarbons found in crude oil are alkanes, cycloalkanes, and aromatic hydrocarbons. Alkanes, also known as paraffins, are saturated hydrocarbons with single carbon-carbon bonds, making them stable and highly desirable for fuel production. Cycloalkanes, also referred to as naphthenes, consist of carbon atoms arranged in ring structures and contribute to the production of fuels such as diesel and jet fuel. Aromatic hydrocarbons contain one or more benzene rings and are important precursors for petrochemical industries that manufacture plastics, synthetic fibers, and pharmaceuticals. Crude oil also contains impurities such as sulfur, nitrogen, oxygen, and trace metals, all of which influence the refining process and environmental impact. Sulfur compounds, including hydrogen sulfide and thiophanes, contribute to air pollution when burned, leading to the formation of sulfur dioxide, a major cause of acid rain. Nitrogen-containing compounds, such as pyridines and quinolines, interfere with refining catalysts and contribute to the formation of nitrogen oxides, which are greenhouse gases and pollutants. These are referred to as NOx and SOx compounds, both of which are harmful air pollutants. Additionally, trace metals such as vanadium, nickel, and iron are often present, posing challenges in refining. Before crude oil can be used, it must undergo refining, a complex process that involves both physical separation and chemical transformation. This topic is very complex and would take days to fully understand, so this will be a brief overview. The primary refining method is fractional distillation, where crude oil is heated and separated into different fractions based on boiling points. Lighter fractions, such as gasoline and naphtha, evaporate at lower temperatures and are collected at the top of the distillation column, whilst heavier fractions, including diesel, lubricating oils, and asphalt, condense at higher temperatures and settle at the bottom. Beyond simple separation, crude oil must be chemically modified to improve the quality and yield of fuel products. Cracking is a fundamental refining process that, as the name suggests, breaks long hydrocarbon chains into shorter ones, which are more desirable. This process involves subjecting heavy hydrocarbons to high temperatures and pressure, causing their molecular bonds to break and form lighter hydrocarbons. Catalytic cracking, a more efficient variation, uses specialized catalysts such as zeolites to facilitate the breaking of chemical bonds at lower temperatures, increasing the production of valuable fuel components such as gasoline and jet fuel. Another essential refining process is reforming, which improves the octane rating of fuels by altering the structure of hydrocarbons. This process is particularly important for gasoline production, as high-octane fuels burn more efficiently and reduce engine knocking. When hydrocarbons undergo combustion, they react with oxygen to release heat, shown here. Ideally, this reaction produces carbon dioxide and water, but incomplete combustion occurs generating carbon monoxide, unburned hydrocarbons, and particulate matter, all of which contribute to air pollution. Sulfur-containing fuels emit sulfur dioxide, which causes acid rain, while nitrogen oxides produced during combustion contribute to smog formation and greenhouse gas accumulation. To mitigate environmental impact, refining processes aim to remove sulfur from fuels before combustion, whilst vehicle emission controls, such as catalytic converters and particulate filters, reduce pollutants. Advancements in fuel technology, including biofuels, synthetic fuels, and hydrogen, provide cleaner alternatives to conventional petroleum-based fuels. Crude oil and its refined products play a vital role in modern society, serving as the primary energy source for transportation, industry, and electricity generation. Gasoline, diesel, and jet fuel-powered vehicles, such as cars, airplanes, and ships, while fuel oils are used in industrial heating and power plants. Beyond its role as a fuel, crude oil is a key raw material for petrochemical industries that produce plastics, synthetic fibers, fertilizers, and pharmaceuticals. Lubricants derived from crude oil reduce friction in machinery, and asphalt is widely used in road construction. Crude oil is a complex and indispensable natural resource, with its chemistry dictating its refining, applications, and environmental impact. Sophisticated refining techniques are required to optimize its use while minimizing its environmental footprint. Although crude oil remains critical for energy production and industrial applications, its environmental implications highlight the importance of cleaner refining methods and the development of sustainable energy alternatives. As always, thank you for watching. If you have any video ideas, comment them below, and we'll see you in the next video.